for the invitation. And so some of you may have seen some part of this talk, and I'm going to try to make it broad. But I will run into some specifics that pertain to my background, which is high energy theory, and I hope it's more or less easy to follow. Okay. But they can ask questions, right?
Sure.
Yeah, anytime, please. Yeah, I mean, hopefully you will ask questions. Okay. So just to set some framework, I guess the main motivation I had as a grad student was that, well, Einstein equations were highly nonlinear, but yet you find all these nice and kind of miraculous solutions to them, given certain assumptions. And in particular, you assume certain, symmetry or supersymmetric vacuum, or you assume the existence of certain ansatz, or say the Kerr-Schill ansatz, and then you find all this catalog of very simple one-line, two-line solutions to these highly nonlinear equations, which have remarkable properties, say integrability, classical quantum integrability, and certain hidden symmetries, for instance. But when we aim to describe more realistic scenarios, we fall short, because each of these solutions, the interpretation is a very particular, not so natural, let's say, background, except, of course, in the case of the Kerr metric, which has an extreme, which is of extreme importance for astrophysics. Okay. So if we refrain from symmetry assumptions, it's extremely difficult to solve Einstein's equations. So there are a lot of theorems involving backgrounds without any symmetry assumption. And of course, one of the most famous works regarding this is the work by Christodel and Kleinerman, which is by now very well known, pertaining the stability or the nonlinear stability of Minkowski spacetime. And of course, there have been a lot of follow-up on this development. And I just want to emphasize this recent paper, which pertains to nonlinear stability of structured black holes, and it's more or less 500 plus pages. So this seems to be a very difficult mathematical problem if we're going to make it rigorous. But we know as physicists, we can use certain intuition to kind of bypass, or at least get some feeling of these properties. And the first instance of that was, of course, the early development by Ray and Wheeler, which showed that under non-spherical small perturbations or linearized perturbations, the Schwarzschild solution was indeed stable. Okay, and this required very little work as compared to the more rigorous and complete theorems that were later proven. And so perturbation theory, which is one of the main tools that we use in high energy physics, actually provides physical intuition and a window into the nonlinear regime. And of course, another famous example of this is gravitational waves, which were first easily derived as a perturbative phenomenon, and then were proved to hold in the nonlinear theory as well. So besides perturbation theory, let me just point out that there are also numerical methods, and currently it's a very natural combination of both perturbation and numerical methods that's been used to construct templates for gravitational wave measurements. And from the perturbative side, things get, of course, increasingly complicated as we aim to be more precise in the Newton. So it's of course natural to get things more complicated as you increase the perturbative strength, and it would be natural to think that there's no method that can escalate as has happened in particle physics. Okay, so in particle physics, there seems to be some kind of bottleneck as we go to 5 or 6 loops in perturbation theory. And then after that, we need to really rely on computer and devise new algorithms. So each method seems to have a certain threshold. Okay, but then there's this new research line that's scattering amplitudes. So of course, scattering amplitudes are the main observables of quantum field theory, so they have been defined long ago. And maybe the myth of this is exactly how we compute scattering amplitudes nowadays. So in the old days, actually, there's a very remarkable result by Duff, who showed that if you take the Schwarzschild solution and you expand it perturbatively, say take the Schwarzschild solution in your favorite gauge, say the harmonic gauge, but you can do any gauge, Schwarzschild gauge, and so on. You expand it perturbatively, and then each of the terms in this perturbative expansion in G Newton, or more precisely in Gm over R, has some interpretation as some Feynman diagram. Okay, this is not very surprising, given that this is basically a wave equation, and there is a source which is the stress energy tensor. Even in the vacuum, there is some self-interaction. So you're solving this wave equation, which is linearized for the perturbative form of Einstein's equations perturbatively. And basically, you can just compute it with prime functions in flat space, and then just compute all possible interactions given the nonlinear nature of gravity, and basically resum all of them. That should eventually give you the Schwarzschild solution if you are away from the Schwarzschild radius. Of course, it's an effective description. And at least it should converge in that region. But of course, when you try to do it term by term, it very much turns into a loop computation. So you need to compute like very complicated iterated integrals every time you go to one more order in Newton. So that seems very complicated for such a simple result, which is the resum version of this, which is the Schwarzschild metric.
Did this have to work?
In a classical sense, yes, you can always compute it by perturbation theory.
It works for Eastern Nordstrom too.
Yes, it works for all kinds of sources. Yeah, so that's a very good question, which is what is the first term in this diagram? It corresponds to a source which has no electric charge or angular momentum. It's a classical source, a point particle. And if you add all kinds of charges, you will explore a wider variety of metrics. But Duff, he didn't argue that this had to work. Of course, he just knew that the metric can be expanded, and that's a general property if you are outside the Schwarzschild radius. And just by explicit computation, he found out that this holds up to, I don't know, probably third order or something.
Does that statement depend on coordinates? Can you not just do this expansion on like ingoing coordinates? Why does it break down at the horizon?
Yeah, so that's a good question. So you can do it, I guess ingoing would be more like a Schwarzschild coordinates. Yes. Yeah, it relies on an effective description of the black hole that certainly corresponds to a point particle. So if you are too close, it should break down. But that's a good question. I mean, it hasn't been computed explicitly in other coordinates.
Could we think of it as sort of more of could we think of it as an indicator that Feynman diagrams properly capture off-shell non-perturbative or all orders off-shell structure and not just scattering states? Is that?
What do you mean by non-perturbative? Like the
I mean, all or not just leading order. Yeah.
Yeah, of course, that's the statement. The full nonlinear theory or the full nonlinear metric can always be regarded as some scattering process in a flat space-time. So that's a non-trivial statement. Even that all we know about this metric is that it's asymptotically flat and solves Einstein's equations without cosmological constant. And the statement is that it can be regarded as perturbation, as a systematic perturbation of Minkowski given by scattering states. But regarding the question of the coordinates, I think, so the goal of this talk is precisely to convince you that we don't need to explore different coordinate systems. And in a sense, the whole deal about scattering amplitudes is that we give a coordinate independent description of general relativity by computing certain observables. And the metric, of course, is not one of them. And yeah. Well, and then there's another question is that, of course, if this is already difficult for the Schwarzschild solution, then what hopes do we even have for two or more black holes, which are more astrophysically relevant? So that's when the scattering amplitudes come to help, or also called on-shell structures. And the goal is that we can determine these on-shell structures by underlying principles. And those principles are locality and unitarity. And that means that we bypass some computations regarding Feynman diagrams. So in the previous slide, the reason that this Feynman diagram, not an on-shell quantity, is that this leg is actually an off-shell field, meaning it's a current. Okay, it's an off-shell current. So it doesn't have a simplification. It means it's gauge dependent. It doesn't have a word identity. So that's the reason that the scattering amplitudes are easier to compute, because they are on-shell and gauge invariant. And so I will try to provide a flavor of how they can help. And I'll focus mostly on Schwarzschild and Kerr spacetimes. So that means I'm not going to cover much about the two-way problem, but hopefully I'll say something about that. So one thing that you may be curious about is treating gravity or general relativity as a quantum theory using scattering amplitudes. We know that there are infinite number of UV divergences. So what do we do with them? Well, the answer is that we take a classical limit, which is low energy. That means we can effectively use GR exactly as an effective description of quantum gravity. We don't need to compute all these non-renormalizable effects. So we don't need these Wilson coefficients. They won't contribute to the Duff's computation. Okay. So these are the amplitudes I have in mind. Roughly, I want you to think of them as a single black hole in this case, being like the red line, and the graviton that's emitting is an on-shell particle, quantum particle, that's gonna represent the metric or the black hole space. Okay, so for instance, in this case, you may have the black hole space-time, but it's being perturbed by a gravitational wave. So that's another way of rephrasing the stability problem. And then there's the two-way problem where you have two black holes, and then there is a gravitational wave emission, and then you can play with more than two and so on. But I will mostly focus on the first part. Okay. How much time do I actually?
A lot.
Okay. So we want to describe gravitational observables because amplitudes are observables and gauge invariant quantities, and the metric is not. So there's one part of the metric which is gauge invariant, which is the radiative piece of the metric, and in fact, the radiative energy and the radiative momentum are observables of the scattering of dynamical processing general relativity. So let us focus on that for now. So we consider a perturbative approach. So suppose we have background that can be expanded as the flat background plus a correction, and this correction can include not only linearized term, but also, all the orders in G Newton that you want. So you can always expand something like that by basically subtracting eta mu. And then basically you take this perturbation H mu and you kind of Fourier transform it, and that can be associated if you go to far times and far distances, meaning to non-infinity. What you get at the linear there is the radiative metric. Okay, and the radiative metric happens to be, if you Fourier transform, the Fourier transform of a current, which is on-shell. Okay, so that's one of the main statements here, that if we take the radiative part of a metric at non-infinity, or even define it in the space-time itself, its Fourier transform in momentum space is basically an on-shell stress energy tensor, and that is very elementary fact of the saddle point approximation as you go to non-infinity. And this stress energy tensor, of course, being on shell, can be associated to a scattering amplitude. So we can think of this as, for instance, two massive bodies, they interact through some gravitons, and then the stress energy tensor can be expanded as well in toward orders in G. And given this effective stress energy tensor, which involves, of course, the pseudo stress energy tensor of gravity of the self interaction of gravitons and so on. Given this effective source, you basically Fourier transform it and get an observable. Which is
the second term with all the complicated lines in it is bundled into an effective term. Is that?
Yeah. Yeah, it's all enclosed into an effective stress energy tensor. Yeah. So this is exactly what you do when you compute amplitudes. Basically, you draw these blobs, and the blobs have all possible interactions, and all these interactions mean basically all different terms that enter in the gravitational self interaction. But they are not gauge invariant until you actually sum them all and get this source. Okay, then what we do with that is basically we extract certain scalars, which are called the byte scalars, which are really just the radiative information of the radiative part of the metric. Okay, so the metric, of course, is a 4x4 tensor, but in the end of it has just two independent components. If you are looking at the radiative part, the way we can extract those components is as follows. So we want to extract them at some point in the celestial sphere. So you can think of this sphere as being the sphere at non-infinity. If we expand the metric at the flat background into these four vectors, it's a tetrad actually, we can project the metric, the perturbation into these components, which are m minus and m plus. So basically, these are tangent vectors to a null sphere. So we take, for instance, the Weil tensor of some perturbation, and then we project them into component plus plus, and then n is just some tangent null vector. That's not going to play much role. But basically, the important part is that we take m plus, or m minus, and that defines two scalars, which are the two components of the radiative metric. Okay, so there is a chiral and anti-chiral component, which are gauge invariant, so they don't depend on which coordinate you choose, and they are because of that observable. And so effectively, what you're doing, if you just write down this formula for H in terms of T, in terms of your stress energy tensor, what you're doing is you're projecting your source into these tangent vectors, which are basically polarization vectors. So your source has two independent components because it has this phi and ward identity because it's on shell, and then you're projecting them into plus and minus polarizations. So these are precisely plus and minus amplitudes of gravity. And let me just try to state that more precisely. And the statement is that the scattering amplitude, which I define in the last line here, is obtained by considering the classical limit of a graviton emission. So let me, if I can draw here. I have one graviton here. That graviton has indices mu nu. And let's say there is some kind of source that emits that graviton. And of course, I can represent that graviton by some kind of amplitude. And then when I want to extract the scalar components, I project them using these vectors m or m plus or m minus. Okay, so these are the two on-shell states of the graviton, and I extract them with these two vectors, which are also called sometimes polarization vectors. Okay, and in the talk, I guess I will use this notation. So I'm not going to explain much what these brackets mean, but essentially, if I take this source, it can be quantum or a classical source. If it's quantum source, then it would be a massive particle. And I need, by the brackets, I mean, I need to take the classical limit. Okay. The classical limit basically amounts to, if I write P, let's say P of this guy, the momentum of this guy, which is m of the particle times is for velocity, basically it amounts to taking m to m over h bar and then taking h bar to 0. So it's large mass expansion. In that case, there is little deflection to the massive source, and therefore the source is classical. Okay. Okay. Please ask me questions if this is not, because this is the main point of this, the first part of the talk. Yeah.
There is a question there.
Yeah, please.
Yeah, so is the classical limit necessary for basically ensuring the m plus and m minus is the same that you'd expect for the background when you're doing this calculation and you do perturbation?
Yes. So if you don't take the classical limit, you won't get the. Sorry, you mean m plus and minus?
Those are like principal null direction.
Yeah.
Yeah.
No. So that is just kinematics. So there is some momentum, which can have this quantum correction, because basically there is some deflection that has to do with h bar, but the kinematical part, meaning the polarization of this graviton is always classical. Yeah. So by classical limit, I guess the only thing that matters is that if this momentum is q and this is p plus q, basically I'm asking that p is much bigger than q. So really, I'm looking at some kind of low energy description of my quantum scatter. Okay, and this goes like 1 over r. So it means like a large radius or radius larger than the mass, then that's when I can do the classical approximation. Okay, okay, well, this is just to say that it can also be done in quantum electrodynamics. Of course, you don't usually hear much about this because quantum QED is just, classical QED is just electrodynamics, and there are all kinds of tools and books on electrodynamics. but it's very instructive to relate both computations in gravity and in gauge theory. The reason being that at the level of amplitudes, those computations are not really that different. Because all the gauge redundancies associated to general relativity basically fade away when you look at on-shell gauge invariant quantities. And that's the spirit of this motto here called classical double copy. Is just the fact that at the level of amplitudes, gravity and gauge theory are really related by a very simple procedure, which is basically squaring the amplitudes of gauge theory. Yes.
I guess, so in a previous diagram, we showed like two black holes coming in and coming out.
Yeah.
And on the previous slide, you mentioned like the algebraic types of space-time. So if you do a similar calculation, like different black holes coming in, wouldn't that be? How do you I guess know the algebraic structure of space-time? Doesn't that like, or you just like assuming that there's like a classical evolution for your current? Like how do you know that the perturbation will change the space-time?
So this holds. Okay, so you're asking about what algebraically, what algebraic types does this hold?
Sorry, sorry, my assumption, I guess like my confusion is I thought so. You said they're like those n plus and n minus are like the null tensions, right?
Yeah.
So are they associated with like the principal null direction?
Yeah. So yeah, of course, this would be all the information you need for type D spacetimes, because you would get like psi, I guess that's psi 4 and psi 0 for psi 4 and psi 4 conjugate by projecting the metric with these two polarization tensors.
Yeah, so if you have like more like, I guess the question was asking if you have like more exotic currents coming in, that you're doing the perturbation like far from the black hole, so you can like assume like a Kerr solution or something, or like a Schwarzschild solution. Yeah.
So we will discuss the Kerr solution. The Kerr solution actually can be fully recovered by this procedure. But for other types of spacetimes, which are generic, not special, say they are not type D or type N, basically you need more information than just amplitude. So you may say, okay, if you have an astrophysical phenomena, two black holes colliding, that's not necessarily type D, it can be type anything. But if at the very end what you're interested is the gravitational waveform of the emitted wave, then actually what you need is only these two components of the metric. So it's enough, even though the space-time is not type D. Okay, so the last paragraph is just a word about the classical limit. I'm not going to discuss much what that means, but there's this word coherent state that, of course, most of you are familiar with, referring to a superposition, a very particular superposition of microscopic gravitons that may lead to a macroscopic metric. Okay, but in practice, it doesn't really play a role because, of course, the coherent superposition is a very particular superposition with very nice properties. And if you do the actual computation by superposing, an infinite number of gravitons in this coherent form, you found out that the result is exactly the same as just considering a single graviton and taking this simple limit. Okay. So, okay, just to give an example how this relation between amplitudes and metrics work. The simplest case is this source, is the sum of the source related to something that was computed in the 70s by Braginsky and Thorne. Basically, it's just the Lie order of a process which scatters different point particles in general relativity. And at Lie order, you find that there is very little deflection and basically the full source just comes from the coupling of gravity to each of the world lines of the particles. So there's no interaction between them. Okay, so this is the source for, say, n bodies, n astrophysical bodies under the influence of gravity.
But this isn't including the Coulomb piece, right?
Yeah, exactly. This is a Line order in R. Yeah,
The Coulomb piece is the same order.
So by Coulomb piece, you mean 1 over R? Is that what you mean?
Well, yeah, this is 1 over R.
Yeah. So that 1 over R, I mean, not the infrared divergence, I mean, not the Coulomb phase, but just the 1 over R term is actually included when you attach the green function. So yeah, we'll see how that 1 over R just appears naturally from attaching the green function. So this is basically the source. So you have to multiply by the green function, which is 1 over R in position.
Is what T mu on the left hand side or H mu?
It's T mu. Yeah. But there's no 1 over R. If it was H mu, there would be a 1 over R. Yeah. So yeah, basically you can just read off the source by looking at their paper. I guess they wrote the metric, not the source. So then there's some correction that has to do with the energy of the graviton. So this is called the soft part. If you go to higher orders in this frequency, you will find that it depends on finite size effects of these world lines, meaning maybe the quadrupole moment of the source, and also on the acceleration of the sources that will play a role as you go close to the event. Okay, but if you look from far away, these effects are really not there at this Line order, and this Line order happens to be universal. So this can be, for instance, black holes or neutron stars. They all satisfy this statement. So if we take just one source, for instance, you will find that there's only one term. Oh, sorry, this I here is just summing our different bodies. If there's only one body, basically you have these two terms. And momentum conservation tells you basically that they can be added. And if you add them, you get a delta function. Okay, that's straightforward. This delta function actually vanishes, so it doesn't have support because, well, sorry, if you go to the regime where K is null, so remember, we're looking at the radiative piece of the metric, so that means in momentum space, we want to make K null. If you go to that regime, you will find that there is no support for this condition. So P and K are never orthogonal if K is null and P is massive. So that tells you that basically there's no radiation, and that's expected because you have a single source, which is just emitting some Coulomb field, and there's no acceleration, and therefore no radiative component to the metric, right? So really, you cannot say much, it seems, about this. In other words, this is zero. But it turns out that if you compute this amplitude in quantum field theory with one massive line and a graviton, it's also zero. So at least that's cool. You have zero on the classical side. There's no acceleration. There's no radiation for a massive source, and you have zero on quantum field theory because this 3-point amplitude vanishes for the same reason that I just said. So there is a match, but it's trivial. But we know that if we allow this to be non-zero, then the radiative part of the metric, which is this thing, will exactly be equal to the scattering amplitude. And this is basic, like elementary amplitude you would compute in quantum field theory. Okay, so the reason it vanishes is that, of course, as I just said, isolated particles have no radiation, but it doesn't have to be that way if you allow yourself to explore something more general than just Minkowski spacetime. And actually in complexified spacetime, that's not the case. If P and K were complex, they can be on-shell and orthogonal at the same time. So if you allow yourself to explore more general signatures, you will find that this actually is not zero, and both parts of the equations are non-trivial and match. So that's the next part of the talk, which is basically exploring 2,2 signature spacetimes. This is a recent work that I did with Andy and Erin and Noah, who are in the audience. And we will refer to the metrics in these spacetimes as Kleinian black holes. Okay, so the main point is that they can be related to scattering amplitudes, and moreover, they can be related to usual spacetimes, meaning 1,3 spacetimes by analytic continuation. Okay, so okay, before I show that, let me just show very schematically how that goes. And basically, the idea is that you can take your favorite spacetime in 1,3 signature and analytically continue one coordinate, which is plus to minus. When you do that, many things happen. And I guess what I wanted to emphasize here is that first, okay, so you have a Penrose diagram, because basically you have time, you have time and space directions, and then you have two compact directions. So you can make a Penrose diagram out of the non-compact directions. And the first thing you notice is that when you do that, the two disconnected components of non-infinity actually merge and become connected. So because time is now basically, because time and position are now symmetric, so there's no distinction between past and future in the same way that there's no distinction between left and right. Yeah.
I'm getting a little lost here. So do Einstein's equations or GR work with two time coordinates?
Yes.
You mean you can just write it down and everything is fine?
If I find you don't mean causality, yes, of course, there is no causality.
Causality I can give up, yeah. But what G mu nu equals P mu nu, and you're saying it all works fine.
Yeah, so you can define complex solutions to Einstein's equations. And by complex, I mean that the metric can be complex. That means there's no definite signature, and you can take different real slices of that complexified metric and get different signatures. But it's all analytic, so it can be computed for complex systems.
If I could just comment, there's sort of a 50-year history now of people going from 3,1 to 4,0. That's why Yao spent his whole life.
Yeah, right.
Euclidean space.
Mhm.
And there's been an enormous amount learned from that, which meant a lot of which was slowly translated into Minkowski space. But one of the problems of Euclidean space, one of the things that you can't study, there's no radiation in Euclidean space. And what sort of happened kind of over the last decade is the realization that it's also interesting to consider a different continuation to 2,2. And the nice thing about 2,2 is you still have radiation, so you can study, and there are many simplifications that also occur. It's a sort of complementary perspective. And so there are a lot of simplifications that also occur
Right.
in
But
2.2, which are now being studied.
But in brief, the equations work for any split of the signature, and then you can analytically continue from 2,2 to 3,1, or as the
That's
case
right.
may be.
That's right.
That's amazing. Okay.
Yeah.
Yeah.
And some very surprising things that happen.
Of course, I can believe that.
Do you automatically know that it can be analytically continued, or is that something?
Oh,
that has to be
sure. I
shown?
mean, that was known probably by Klein was in the 19th century. He was studying. I don't know when that was, but the Einstein equation. Riemann wrote them down, and it lowered over. It was Einstein who decided it was interesting to study them in 3,1, but just as a mathematical system, it seems to have. Well, it has very miraculous properties in 3,1, like positive Levy energy. It has other miraculous properties in Euclidean space. The thing that, the proof of the Calabi conjecture, that was all Euclidean. Not only that, any number of Euclidean dimensions. But the 2,2 is a sort of a brand new thing, and in a way almost more directly related to dynamics in Minkowski space, because there is scattering theory. And so that's what,
Yeah, so at the linear level, which is what I'm probably going to focus here, that's just a property of the wave equation that can be solved for complexify solutions and then analytically continue, that the Lambertian operator can be analytically continued to Laplacian and so on. And I guess the real need of the continuation is in the boundary condition or in the initial value problem. Really, there's no intrinsic definition of initial value problem, as far as I'm aware, in 2,2, and these are ultra hyperbolic PDEs. But we don't aim to set an initial value problem, but simply to extract all the physics from the Lorentzian problem and then analytically continue that. So our notion of causality is just what follows from direct analytic continuation of 1,3 spacetimes. Let me just say, very briefly, that in 1,3 space, basically there's two disconnected pieces to null infinity. If you take, a Lorentz transformation here is basically a rotation. So you can go from one point to its antipode point, and a Lorentz transformation in these two coordinates would be a boost. So it doesn't allow you to go from past to future. But if you kinetically continue one coordinate, of course, there's no boost anymore, but just simple rotations. So that means basically that you can go from past to future via a continuous transformation. And that's the whole point of this merging that occurs with non-infinity. Basically, you have two celestial spheres, and after analytic continuation, they both merge into torus for the two compact coordinates. That's what we call the celestial torus. So you can do that for these different spacetimes. The first one is a linear similarity, basically just linear structure with some point particle emitting some Coulomb field. If you do that, there's a surprising fact that the Coulomb field actually goes to null infinity instead of just special infinity. So basically you can describe this Coulomb field in 2,2 as being composed of just radiative, quote unquote radiative modes in 2,2. And I really want to emphasize this because this is one of the main points of this part of the talk, that even a stationary Coulomb or a stationary point particle after analytic continuation actually can be described in terms of radiative modes.
So no acceleration needed.
Exactly. So because of that, that can be described, as I already anticipated, in terms of scattering theory. And so you can do that for Churchill, the full nonlinear Churchill. Actually, you get something very simple here. Basically, you get what you would expect for Euclidean Churchill. The horizon, the curvature singularity just hides behind this horizon. You also get one single component, non-infinity. And maybe the more important or interesting ones are the self-dual solutions that are new in this signature. You don't have self-dual solutions in 1,3. The reason is that, of course, self-dual solutions are defined by this condition. And in 1,3, this automatically implies that you have a complex metric because the eigenvalues of this operator, the Hodge dual, are I and minus I, but here are just -1 and 1. So this new class of real solutions only emerged in 2,2 signature and actually have very remarkable properties that are completely invisible in 1,3, as I will just show. And moreover, they are related via analytic continuation to certain solutions in 1,3.
So just for the second diagram, are we supposed to understand that there is some extension beyond the left-hand side? R equals 2n?
Here?
Yeah. Is the diagram you've drawn a subset of the full diagram? Or
No,
is this the full diagram?
That's the full diagram. Yeah. So it's just as the Euclidean case, there's no extension beyond the horizon or R equals 2n. Yeah.
So for the self-dual solutions, we said that they would continue most naturally to complex metrics from 3,1. So do they still encode? So in what manner do they encode physics in 3,1 for real metrics, or what do you do with them to learn about 3,1 physics?
Right. Okay. So in the Euclidean, I guess in Euclidean signature, these are just subtle points of the path integral, and that's already physically relevant. But of course, in 1,3, they are just complex. They are just complexified solutions. And but it turns out that they belong to a wider family of solutions, which are the general top knot solutions that actually encode the curve metric and other cases. But yeah, so in 1,3, by themselves at this very specific self-dual point, I don't think I'm aware of an interpretation.
Okay. Well, it's just like Kerr, right? In Euclidean Kerr, if you naively continue, you get a complex.
Yes.
So you have to continue the angular momentum, which there's good physical. You do that even in quantum mechanics, right? So here you can continue this complex solution, but it continues back to, depending on your procedure, you would probably get toughened up.
I see. So you're saying there's other parameters you can continue along with. So that you get.
There's 4 parameters.
I see.
In 2,2, the nut charge and the ADM are on the same footing.
Yeah.
So depending on your prescription for analytic continue, you would typically end up with something with nut charge, ADM mass.
Gotcha.
And angular momentum.
But that leads to a wider family of solutions. At the self-dual point, you really get a complexified metric in 1,3.
Does Schwarzschild look like a radiated spacetime in this signature? Does it look like?
Yes.
It does.
So that's what I was mentioning here. Although this was only for the linearized case, you would get this form of the Fourier components, which are actually on shell, meaning they are going to non-infinity.
So, I mean, why does this happen? Is it because the Gauss constraint now has a time derivative instead of 3?
Yeah, that's probably a good intuition, but that's so. one way to say it is that this is really the most symmetrical setup that you can devise with 2 times and 2 position coordinates. So there's no reason why the field of a stationary source would go to special infinity. Okay, so just to give you a flavor of how this works, that now that we are into 2, as I said, we can compute amplitudes into 2. These 3-point amplitudes do not vanish. They do vanish in Minkowski signature. If you do that in 2,2, you get the same answer. Basically, you can compute your amplitude in complexified space-time, and this is the answer for any signature. The difference is that, of course, this delta function now has support, so it doesn't vanish. And so the amplitude is not 0 in, say, 2,2. Moreover, if you include a spin, which encodes some finite size effects of the source, you can do that by attaching a spin to this quantum particle here through the so-called Pauli-Iwansky spin vector. So it has some angular momentum quantum operator, and then there is some vector defined for it, which defines the little group of states and so on. So this Pauli-Iwansky vector basically represents the spin magnitude of your source. If you compute this amplitude for some particle with arbitrary spin, say higher spin, you will find that for particles which are minimally coupled to gravity, this spin operator exponentiates. Okay, and that was one of the results from these papers. So the fact that it exponentiates automatically tells you that there is something very simple about this amplitude, and that simplicity is actually nothing but the no-Hertz theorem of general relativity. And in fact, this is nothing but a very particular form of the Kerr metric, as I will now show. Because of course there is no other parameter that will enter here. There is no quadrupole and so on, like effective Wilson coefficient. So if the only thing you have is a spin in the minimal, which is if the only thing you have is a spin, what you're gonna get is just a black hole. Okay, so to make this precise, this is one form of the Kerr metric, which was found basically by Newman and Janis after a couple of years that the Kerr metric was published. And it amounts to describe it as a deformation of the Schwarzschild metric by some differential operator. So this differential operator effectively acts on the coordinate r, and it shifts the coordinate r by an amount of a, which is this spin vector. Okay, so this is cosh, and then there is this sinh of a dot delta. So there are different shifts of this r. If you resum this full series, you will get basically the Kerr-Schild form of the Kerr metric. Okay, and now what we can do in 2,2 spacetimes is to extract the self-dual and the anti-self-dual components of this metric that you cannot do in 1,3. But in 2,2, if you do that, you would get these 2 terms. Okay, and if you add these 2 terms, you will get the first line. And the 2 terms differ simply by a sign on the spin. And the explanation of that is that, of course, the spin is a parity odd term, so it will flip sign if you change chirality. Okay, so basically these 2 terms correspond to plus and minus components of the Kerr metric. But now we can see basically that this form of the metric is nothing but the same as this amplitude. If we ignore these polarization states, we have the exponential of the spin dot k, which translates into this a dot del, and then the p nu components of Schwarzschild, which translates into these components, which are the form momentum basically just time direction, the killing direction of the Schwarzschild metric. And this is just a green function, so it's all encoded in the propagator after I convert this to a metric. Okay, so one more of the story is that there is some gauge invariant components here, some classical observables that correspond to scattering amplitudes. You can extract those from the metric by doing this projection into polarization tensors. And the second moral of this story is that relating this to scattering amplitude actually reveals new properties of the Kerr metric or the Selfdual components of the Kerr metric. So the first property is that the relation between, Schwarzschild and Kerr is basically a shift by amount of the spin. So in the Selfdual part, which is basically just picking a sign here, say plus, I can obtain the spinning metric from the non-spinning one by simply shifting the coordinates, okay? And that's, I'll come back to you. That's just a new statement about these metrics that holds in 2,2, and it's completely invisible in 1,3, although there have been different approaches to it, particularly by Newman and Janis, using complexified shifts, okay? So we refer to this statement as the fact that top knot, which is the self-dual piece of this Schwarzschild metric, is diffeomorphic to Kerr top knot, which is the spinning version. Yes.
So is it that, so this H mu, this is the result from the scratching amplitude of the previous, so the scratching amplitude of the previous slide is equal to this H mu?
Yes, basically, yes.
So and that's for Kerr, so it's like non-radiated in 1,3, and it ends up being radiated in this 2,2.
Yeah.
And this is like similar to doing the Janis-Newman algorithm somehow.
So the Newman-Janis algorithm is just an algorithm. It's not a coordinate transformation.
Yeah. So I've seen supposedly. So I've seen supposedly if you consider, you can supposedly, okay, I said that 3 times. Anyway, you can consider it as a coordinate transformation if you consider, say, a complex manifold. It's a complexified 3 plus 1 instead of just like a real 3 plus 1. And then the algorithm is somehow a coordinate transformation, then a projection in that manifold. I mean, it's not truly a coordinate transformation because it's a projection at the end of it. But
it works, the Newman-Janis algorithm works in a very particular frame. And the reason for that is basically that you need to shift these 2 coordinates R. You need to complexify your metric as a function of R and R conjugate.
Yeah.
And then you need to decide which R's to make R's and which R's to make R conjugate. All that ambiguity is not present here when you split the metric into self-dual and anti-self-dual components. And you can just shift the self-dual piece by this coordinate transformation, which is a truly genuine coordinate transformation and not an algorithm. But they are at least mathematically related.
yeah, it also seems kind of interesting because the Newman-Janis algorithm, you can't go back. Like you only goes one way. Like are these scratching amplitudes in the 2,2 like type? Like you don't really, I don't know. Can you flip it back in a similar way, or flip it back so that I guess is there like somehow a mapping from Kerr to Schwarzschild instead of just a mapping from Schwarzschild to Kerr? Yeah,
it's just the inverse of this transformation, but that can only be done at least explicitly for the self-dual case.
Yeah, we should conclude in about 10 minutes.
I'm about to. 10 minutes?
Yeah, I'll just start a bit later.
So can I ask a question?
Yeah.
Maybe we let him finish.
Yeah, I mean, there is not much to say, I guess. Not much more to say, except that, well, I talked a lot about these 3-point amplitudes, and you may be curious how they are, computed without Feynman diagrams. And in fact, it's a very general theorem that you can basically compute these 3-point amplitudes by looking at how they transform under Lorentz group. So just the little group transformation of the 3-point amplitudes basically fixes them completely. There are no other there are no other 3-point amplitudes that transform in the way they should. In the case, okay, let me just say, in the case where all particles are massless, but we know that this massless amplitude is very simply related to the black hole amplitude by something which I told you about, which is the minimal coupling. So this is all just to say that you can basically compute this without having any notion of a Lagrangian or of Riemann diagrams. Okay, they are just fixed by Lorentz invariance. And then you may ask what happens here if you have a 4-point amplitude, and then it turns out that they are not fixed. Of course, you can have contact terms and Wilson coefficients and so on. So I'm not going to explain exactly how to compute them, but I'll just say that they are basically related to perturbations. As I said, they are basically related to a perturbation of a black hole background, where I perturb the black hole background by a gravitational wave or a massless wave of certain helicity. Okay, and those perturbations, they can be evaluated by solving the Rayleigh-Wheeler equation for Schwarzschild background in classical general relativity. We can, instead of solving the Rayleigh-Wheeler equation, which amounts to perturb a black hole, we can basically apply the second quantization rule and replace the black hole by some kind of particle, massive particle. Okay, so that's effectively what we are doing when we say that these 4-point amplitudes describe perturbations of a black hole. Okay, I think, and of course you can do this for different perturbations. You don't always need to perturb by gravitational waves, but you can perturb by a neutrino wave or a scalar wave, and that amounts just to compute different 4-point amplitudes for scalars or gravitons or fermions. Okay, that would be it for now. Yeah.
Thank you. Maybe we have time for one question and we continue over lunch. Razi, you had a question? Huh? She disappeared.
Oh.
That was a wonderful discussion. So I have a question regarding to this exponential improvement or the solution of the scattering amplitude. I wanted to know, does that what is the physical meaning of that? If you have a particle that is actually moving along the black hole spin versus on the opposite direction, are you saying that these are going to be exponentially improved or exponentially down? If that's really the case, then we can just easily actually use that, by just launching some particles and see what we get, and that will be maybe proof of your theorem, or am I missing something? I should also accept that as a slightly late in your talk.
Yeah, so there are two things. Yeah, that's also. So there is this thing. Okay, I just write it there. So this thing amounts to for a stationary space-time that emits certain radiation. And by radiation, I really mean the metric. Okay, so this is in 2,2. So really, all this stationary solution is encoding this radiative component, and that's basically up to a factor is exponential. So that means basically that the metric itself is translated or is displaced by an amount of A with respect to the non-spinning metric. Okay, so this amounts to shifting the metric by A. Now, what you're asking is basically a different scenario where I have a particle, and then I have a background, say a black hole, and then I have a perturbation, which can be, let's say, a geodesic or a massive particle traveling in this background. Okay, so that would be a different amplitude. Perturbation can be a wave, as I just said, or it can be a massive particle, and in fact they are related by something that's called the Conant limit, that basically allows me to compute the geodesic, basically solve the geodesic equation by solving the wave equation. So if I consider this kind of perturbation, this amplitude actually has two factors. One of these factors is the first amplitude, which is exponential of A of K, but then there's this other kind of 3-point amplitude. That's really, it's not universal, but depends on the type of particle you scatter and so on. So what happens is that there's some exponential structure, but it pertains to the metric itself, not to the massive particle.
So K here is which momentum?
K is the inverse of, so K is momentum transfer here. So it's the inverse of the radial distance between, the source, say the black hole and the particle. Yeah, we can talk more about that. It's a very interesting problem.
So actually, one very quick thing.
Yeah.
The first thing you said, this translation by A.
Yeah.
Takes you from short shield to curve.
Yes.
I'm immediately confused because you've got a 2+2 signature, and I can put A in either the plus signature part or the minus or a mixed. Are you saying they're all curve of some kind?
Oh no, so A is always, sorry about that. So A is always the space, some space direction.
One of the two space directions.
Yeah.
Okay, fine. And
Yeah.
what, is there a meaning to putting it in the time direction?
So what A has to do is to be parity odd. What that means in 2,2 is that basically it has to flip sign if you invert a time direction. I guess that's the reason that it cannot have any symmetry. Yeah, but it's a good question.
So the really final thing is that this factor is just going to be the same for a scalar particle, like a vector particle, or actually spinors that are around this black hole.
No, you will have to, so here you will plug, if you really want to solve this geodesic problem, at least perturbatively, you will plug in whatever your corresponding amplitude. If your point particle has, a spin or other degrees of freedom, you will have to attach an amplitude which has, spin.
Right, but I'm just saying the exponential A dot K.
No,
That's just coming from a space-time.
Yeah, that's universal.
It seems to be okay, perfect. So there's not any symmetry depending on the spin of individual particles that pass by, but that's just entirely from K.
That's true.
Okay.
That's true. So in a sense, you would take a geodesic in Schwarzschild, apply this shifting procedure, and get a geodesic solution in Kerr, or at least in the Selfdual.
All right, let's thank our speaker again.